Welcome to the Mathematical Physics seminar in Prague. Our speaker of this week is Felicia. She's a first-year master student from Ferraioli, which is like a small city close to Naples. And she's going to give us a gentle introduction to algebraic operands. Please.
Okay. Good afternoon, everyone. My name is Felicia Ferraioli. Thanks so much for introducing me. And today I will give a seminar titled A Gentle Introduction to Algebraic Operands. First of all, I would like to thank Thomas for inviting me, and also for the organizers and hosts here in Prague for their warm welcome. And I also would like to thank, of course, my supervisors, Professor Chiara Esposito, who today is here with me, Professor Luca Vitaliano, and Dr. Martin Dippen, because this talk is based on my bachelor thesis in mathematics at University of Salerno, and they helped me a lot. I think today I will talk about algebraic operands. It is a really powerful language which allows us to describe operations and the laws of their composition, and it also provides a unified framework for algebra. I don't know, but you might have heard that operand theory is in a way just language, and I think that probably it is in a way. But as I hope to show you today, it is a powerful language because it allows us to see connections where before we saw just like separate structures. So it's powerful, and I hope to show you this today. My goal today is to provide an entry point, the theory of algebraic operands. Often, this theory is introduced from a very advanced, abstract, and categorical perspective. But today, I will take a more pedagogical approach. So I will build the theory from the scratch. We will start from the very first definitions, and then we will arrive to state the three main isomorphism theorems, which are about the three bases of algebra: associative, commutative, and the algebras. And so that's the plan. First of all, the main definitions and the core motivation of the theory. Then we will talk about Operads trees, which are powerful tools in order to see composition and operations in a visual way. And they are also the building blocks of the pre-opera, as you will see later. Then we will meet the first two bases of algebra, the associative and the commutative one, the commutative algebras, which are encoded by these two operands, as and com. And then we will need generators and relations in order to introduce the third base, the operand V, because we struggle if we try to define it with the classical definition and the classical way. And okay, so a small disclaimer before we dive in. Since this is a pedagogical introduction, there is the risk that sometimes it might feel like a paradox definition, and I apologize for that, but we need this technical part in order to define the three bases of algebra, and then I hope that I can show you which kind of objects we can recover by means of this formalism. So I will try just to give you an idea that there is a lot to say. Okay. Let me start with this quote by Henri Poincaré. Mathematics is the art of giving the same name to different things. I like it very much because I think that it really captures the spirit of operatic theory, because in algebra we have many different algebraic structures like monoids, rings, algebras, which at first glance look very different, but when you look at them from a more abstract perspective, then you see that they share common properties like the existence of an associative multiplication or a unit. And so we would like to give them the same name, and we actually do it by means of operatic language, because we can call them, we can name them algebras over a specific operand. So we managed to do this by means of operatic language. And the nice thing is that when you set up the right operand, then you can do proofs. And when you prove something at an operatic level, then this proof is valid for any algebra over that specific operand. So it also simplifies proofs and statements, and it is a really powerful language. But if you don't trust me, you can trust, for example, the groundbreaking results achieved by means of operatic theory in algebraic geometry or beyond. For example, there exists a famous proof of the formality theorem by Maxim Kontsevich, the one from Tamakin, which employs the language of algebraic operads with something related to L-infinite algebras by employing the resolution of the Beetle-Bisque operad, which is an advanced example of operads. And we will not focus on this today, but it is just to give you an idea of how powerful this formalism can be. And it has a lot of applications in physics, in mathematical physics, in string theory, a lot, really a lot. Okay. Now we will talk about the core motivation of this theory, which comes from representation theory. In classical representation theory, we study an algebra A by letting it act on a vector space V. In this context, the representation of an algebra A is just an assignment which assigns to each abstract operation in the algebra A a concrete linear operator over the vector space V. But that's the key point. NP only contains unary operations, so with one input and one output. What if, for example, you want to model a multilinear operation or a Lie bracket, for example? Then you will need another target. Then you have to consider the whole family of multilinear maps from V tensor N to B, which is not just a family of vector spaces, but it comes with a rich structure, because it comes with a natural way to compose multilinear operations. When you have a multilinear operation, you can just substitute its inputs with other multilinear operations, so exactly like substitution, and it is completely general and natural, and it also has nice properties like it is an associative composition and it has a unit, the identity map. So when we give the definition of an opera, we would like to mimic these kind of properties, and it is exactly what we are going to do. So in this context, a representation of an opera P is precisely this kind of assignment. So it assigns, again, to each n-ary operation in the opera P, abstract n-ary operation, a concrete multilinear operation into the Operads of homomorphisms. So when you think about an opera, you just have to think about operations and composition, nothing else. It is very, very easy, and once you understand this, it is completely, yes, easy. Yeah. So that's the slogan, Operads generalized representation theory from unary to multilinear operation, that's all. So let's begin now with a simple setting, which is the non-symmetric one. I would like to show you that with a very few tools, we can already recover complex structures. Here is the definition of a non-symmetric opera. It is just a family of sets or vector spaces, or more in general, objects from a symmetric monoidal category. But now we will focus on the case they are vector spaces. In this case, we say linear operads, because this is what we are, what is near to representation theory. So it is the case we will focus on. And it comes with composition maps, which are linear in case of linear operads, and something that they satisfy associativity and unit laws, which are the obvious one. And yes, in order to make everything more complete, we can immediately look at the proto example of non-symmetric opera, which is the Operads of homomorphisms. And it is exactly the structure we mentioned before. So here we set NBN exactly equal to the space, the vector space of multilinear maps from V tensor N to B. And here we define composition exactly by substitution. So when you have a linear map F and you have n multilinear maps G1, G2, Gn, then you can just compose them, and then you have a new multilinear operation with K1 plus Kn inputs, which are the sum of the number of inputs of G1, G2, Gn. And when you apply it T1 of Tn vectors, you just have to apply Gi to its own block of inputs. Then you take the outputs and you feed them into F in order to obtain the final result. So it is very, very easy. It is exactly substitution. And here, of course, identity, the unit is obviously the identity map. And this example will be crucial in the following because the endomorphism operad is the target of operad representations, as we see now. So, first of all, now that we have understood what an operad is, we would like to understand how they communicate with each other. And now we define what a morphism of operads is. And it is the obvious definition because it is the analog of a morphism in like every algebraic structure. It is just a family of linear maps in case of linear operads, which preserves composition and unit. So it is a structure preserving map, the obvious definition. And okay, so with these abstract definitions we have given, now we would like to understand why do we need this and what do we do with those definitions. And so we have that our P algebra is the concrete realization of this definition because it is exactly the assignment we mentioned before. It is a morphism of operads, and it is the assignment which assigns to each abstract ternary operation in the operad a concrete multilinear operation now in the operad of endomorphisms. And again, when we have words, we would like again to understand how they communicate with each other. And so here we define what a morphism of P algebras is, and it is again a structure preserving map. Here we have that a morphism of P algebras is a linear map from a vector space V to another vector space W, such that this identity holds, which is very simple. It is just saying that if you apply an operation and then you apply F, it is the same that applying F to all the inputs of the operation and then applying the operation in W. So it is easy. And P algebras with morphisms of P algebras form a category, the category of P algebras. This is my notation for this category. And it will be very important in the following because the theorems we will state are isomorphism theorems of categories, and this category will be crucial in the following. So keep it in mind. So, so far we have considered the simple setting in which permutations were not allowed, but sometimes in algebra we have algebraic structures in which the order of inputs of an operation either does not matter at all, or it matters up to a sign. For example, in the V case, in which we have skew symmetry, for example, so we would like a way in order to control symmetries between the inputs of an operation. And for this reason, we would like to find a way to swap the inputs of an operation. In the operator of endomorphism, we have another way to swap the inputs of an operation, and it is by a right action, thanks to a right action of the symmetric group on each base, which works like this. And we would like to have a similar action in the operand setting, and we actually have it. And we have the definition of a symmetric operand. Now I would like to show you that with just one more new ingredient, we can recover commutativity, we can recover skew symmetry, and so the power of our language increases really a lot. And the definition is actually very simple because a symmetric operand is just a non-symmetric one in which, in addition, we have a right action of the symmetric group on each space for proportionality, and we have that substitution has to be equivariant. So we we have this formula here. I know that it can look a little bit difficult to read, but it is really simple because it is just saying that if you that composing and then permuting is the same that permuting and then composing in the right way. But then if we will have enough time, I can come back to it after introducing operatic trees, and I can try to give you a visual representation of this formula, which is actually very simple and natural, easy to understand. Okay. So the moment is now. And I promised a gentle introduction, and so let's take a break from abstract formulas. This is exactly where our language becomes concrete. Trees are really, really powerful tools because they give a visual, graphical representation of operations and in a very precise way. And they will be the building blocks of the pre-operads, so they are not just pictures, as we will understand now. Here, there is a definition, a working definition of operatic tree. Let me stress that this is just a working definition because the real one is very technical, and we have to care about a lot of details, and we struggled a lot in order to formalize it. But I think that today the only important thing to understand is how trees manage to represent operations and composition. That technical details is something which come later, in my opinion. But if you are interested, then we can, of course, I can give you more details. Okay, so you can think about an operatic tree just like this one. In this kind of picture, vertices are the operations, correspond to operations, and the upper edges are named leads, and they correspond to the inputs of an operation. And unique root, which is the lower edge, is the output, the unique output of the operation, because now we only consider operations, multilinear operations with several inputs and but one output. So tree is exactly a picture like this one. And here you can see a few examples of trees. The first one is named trivial tree, and it has no vertex. It has just a single root which identifies with its unique leaf. So it is an operation which does nothing, and it corresponds to the identity, to the unit of the operand. Then we have the stump. The stump has a unique vertex, the unique root, of course, but no leaves. So it corresponds to an operation with no inputs, but a single output. So a constant element because it takes nothing. And then you have N corollas, which are trees with a single vertex and leaves and one root. And so they are the most natural way to represent n-ary operations. And then by composing them, we can obtain bigger trees and more complex ones. And trees are not just pictures, but they can be composed in a precise way. And we can define a composition of trees, which is by grafting. Here, composition is just grafting. When you have a tree G0, then you can compose it with other trees. If the tree is G0, like this one, with say n leaves, and you have n other trees, like say G1, G2, Gn, then you can compose them by gluing the roots of G1, G2, Gn onto the leaves of G0 in their order, in the non-symmetric case. And in this way, you can obtain a new tree which corresponds to the composite operation, and everything can be formalized. Well, this is just a picture, but it can be formalized very carefully. Okay, so finally, let me stress the difference between planar and non-planar trees. A planar tree is a tree which possesses total order on the leaves, and it can be thought like a bidimensional tree, because if you have a bidimensional tree on the paper or on the blackboard, you have an order, the obvious one, the one from left to right, and you cannot change this order. But then you have, on the other hand, you have the non-planar trees are trees in which we do not have this order, and they can be thought like trees embedded in a three-dimensional space. The proper example is probably our hands. We have the wrist, which is the root of this kind of tree, and then we have the leaves, our fingers. And if you look at it from a perspective, then you see an order. And if you look at it from another perspective, then you see another order on the leaves. So if you want to draw it in the plane, then you have to choose an order, and it is what we actually do. For example, if you have a three non-planar corolla, for example, then you can draw it on blackboard, and you have to choose an order, because here we have the canonical order, the one from left to right. But what we do in order to draw the other possible embeddings of these three corolla is labeling the leaves by means of integers, 1, 2, 3, and then we can draw the other possible embeddings just by commuting the labels onto the leaves. So, for example, this is another possible embedding, but then you have 6, of course, the number of elements of the symmetric group of 53. I think it is really easy. And this is also the natural way to define a right action of the symmetric group onto a tree, onto a non-planar tree, because planar ones correspond to non-symmetric operads. So there we do not need to define a right action, but if we have a non-planar tree, we can define a right action of the symmetric group just by swapping, by commuting the labels onto the leaves of the tree. Of course, and yeah, thanks to these definitions we have provided, we can now probably understand in a more visual way this formula. This is the equivariance formula we saw in the definition of symmetric operand, and I think it can be easily understood by means of trees. Maybe I can explain you a little bit more. Let me consider, for example, a binary operation, say theta, and then we can consider theta1, a ternary operation, and theta2, another ternary operation, and then we consider maybe sigma, a permutation of two elements, 1, 2, 2, 1, and P1, a permutation of three elements, for example, 1, 2, 3, 2, 3, 1, and P2, another permutation of three elements, for example, 1, 2, 3, 3, 1, 2. Okay. Then the left-hand side of the formula is theta dot sigma, composed with theta1, theta sigma 1 dot theta sigma 2 dot sigma 2. And when we draw it, when we can picture this kind of formula by means of trees, of course. This is a binary operation, so we can draw it like a two corolla. theta dot sigma. So with two leaves, and we can label them by means of integers 1 and 2, of course. Then on the first, we have theta 2 because sigma 1 is 2, and dot p2. And the theta 1 dot p1, and they are ternary operation. So operations are 3, and so they are 3 corollas. But then if we apply permutations, here we have theta with the inputs swapped, 2 and 1. On the second leaf, we have theta 1, which is a 3 corolla, but now the leaves are permuted according to E1, so 3, 1, 2. And here, leaves are permuting according to P2. So
this is not
yes.
yes.
Sorry.
This
Yes. 2, 3, 1, 3, 1, 2, because this is P2, this is P1. I saw it. And now we can identify it. Okay, thank you. We can identify it with 6 corolla because it has 6 inputs. Say theta composed with theta 1, theta 2. And then we have inputs ordered in the obvious way. So we start from the first leaf, and then we read 1, 2, 3. And then 4, 5, 6, in this way. But on the other hand, so if we look at the right-hand side of the formula, here we have theta composed with theta 1, theta 2, dot sigma composed with phi 1, phi 2, where this is the block permutation of symmetries. I don't know if you are familiar with it, but I usually draw it like this. Here I write integers 1, 2, 3, 4, 5, 6 because I expect to have a permutation of 6 elements. Then I apply P1 onto the first block of integers. So here I have P1, which is 2, 3, 1. So 2 goes to 3. Sorry, 1 goes to 2. Then 2 goes to 3, and 3 goes to 1. Then I apply the P2. 1 goes to 3, U1 is 4, of course. And 2 goes to 1, and 3 goes to 2. And then we apply sigma to the 2 blocks. So this is the first and this is the second. So 1 goes to this way. And we have exactly the same permutation because 1 goes to 5, so it is the permutation 5, 6, 4, and 3, 1. So it is the second sum. So, of course, everything works here. Everything works here because trees work themselves an operad, which is the operad of trees. So of course they satisfy the equivariance law, but in general we just impose with this kind of law. But here everything works in a very easy way. And okay.
Maybe I have a quick question. So,
yes.
like here, things are I mean, rather easy, right? Because you have linear maps. But like in general, one has to be a bit careful with the composition. Like here, I guess you're asking this to be associative, like in a horizontal and in a like vertical sense, right? So if you go to the like previous picture, composing like horizontally or vertically,
Associativity is kind of obvious.
exactly, it's just linear
Yes.
maps.
First, also because associativity in the tree setting is just that if you draw first the root and then you glue trees over there, you obtain the same result than maybe drawing first one thing and then another. So it is obvious, but I think it is obvious in every setting because everything is similar. Because the tree representation is the same, even if you consider a general symmetric model category. Then
It's naturality.
yes, the way you when you graphical represent your graphical picture, it is the same. So I think that in this setting, associativity is obvious. It's like right. And okay, so now we are finally able to meet the first two grades of algebra, associative and commutative one, which are encoded by these two famous operads, the operad as and the operad comma. The first one is the operad as. I want you to notice how economical this structure is because it is incredibly small. It is small arity-wise, of course. It's just one-dimensional in each arity, but this tiny object is exactly what we need in order to encode associativity. And I think it is like, I don't know, incredible how powerful just the operations and composition can be this kind of language. Here we set as 0 as equal to 0 because here we do not need zero arity operations because here we do not need a unit in associative algebra. We do not necessarily have a unit. And then we set as n as isomorphic to the field k because in an associative algebra we have just a canonical way to multiply elements without caring about parentheses and parenthesization. Okay, and here composition is exactly the canonical product of scalars in the field K, and everything is very, very easy. And the really cool thing, I think, is that now we have this theorem which says that the category of associative algebras is exactly the same because it is isomorphic as a category to the category of algebras over the operad as, which is the category I mentioned before. And the proof is really, really easy, and I would like to show you it because I would like to convince you that it is super easy. There is no difficult stuff in this setting. It is just linear algebra, so it is really easy, and I think it can be understood by everyone. Maybe I have to erase.
You could also use the second blackboard if you want to.
Kind of with
Then this will be blocked. Yeah.
okay. And yeah, it's fine.
As you like, I mean,
As you like.
otherwise you have to clean it.
Okay.
But I think it's readable.
Okay. The proof is by constructing two factors, because here we would like to prove an isomorphism of categories. So we have to construct two factors, a factor f from the category of algebras over the operad as to the category of associative algebras over the field K. This is my notation. Then we will check that everything is well defined, so that f is well posed on objects and morphisms as well. Then we will define a factor in the other direction, say G, from the category of associative algebras to the category of algebras over the field K. And again, we will check that G is well posed as well. And finally, we will check that F and G really under each other. So first of all, we can let me start from by. Let me recall that this category is made of algebras. So an algebra can be thought as like a couple VP, where V is a vector space and phi is a morphism from the operand S to the endomorphism operads over the vector space V. So here V is this kind of morphism. So given this morphism and F morphism of our algebras, we set F of V P as equal to the couple V and V, where F and V is set as P2 of mu2, where here P2 is the second map of this family. This is a family of maps. And mu2 is the unique generator of the operand S in IT2. And we set F, we define F on morphisms to like the identity. So if we have F a morphism of us algebras, then we just define F like the identity. Now we have to check that F is well defined, is well posed on morphisms and objects as well. So we have to check that MB is bilinear and that it is associative. MB is bilinear by definition because it is an element of MB2, so it is clearly bilinear by definition. And in order to check that MB is associative, we can consider this equality here, mu2 composed with mu1 times mu2 is equal to mu2 composed with mu2 times mu1, where here mu2 is again the unique generator of us2 and mu1 is the unique generator of us1 and unit of the operand. We have that this identity holds because S is one-dimensional unitarity. So if we compose generators in this way, we obtain the unique generator of S3 in both cases, and so this identity must hold. And then if we apply phi to both the terms of this inequality, then since phi is a morphism of the operads, it preserves composition and unit. So here we have P2 or mu2 composed with P1 or mu1 times P2 or mu2 equal to P2 or mu2 composed with P2 or mu2 times P1 or mu1. But here, by definition, P2 of mu2 is MV, the multiplication, the associative multiplication we are trying to define. Composed with, here we have the identity over the vector space V, because phi is a morphism of operads, so it preserves identity, the units of the operad. And tensor MV is equal to MV composed with MV tensor the identity, which is exactly associativity. And last thing we have to do is to check that F is well defined on morphisms as well. So if we have F, a morphism of algebras, then by definition, I do not have it here, but by definition, it satisfies this equality for each arity. Here we have that F composed with E and B of mu n is equal to E n in W of mu n composed with F tensor n in each arity n. But if we consider this equality in the case n is equal to 2, here we have this equality here, and here by definition, P2 of mu2 in V is NB. Here, sorry, Phi2 of mu2 in W is NW, the multiplication in W, the associative multiplication, composed F tensor 2, and it exactly says that F is a morphism of associative algebras. So everything is well posed. Of course, we also have to check the factorial identities, but they are obvious in certain to define like the identity on morphisms. So it of course preserves composition of morphisms and identity. And yes, so F is well defined. Okay, so now let's start with G. In order to define G, we have to consider an associative algebra A and A, where MA is the associative multiplication, and F a morphism of associative algebras. And we set G, A, and A as equal to A psi A, where psi A is defined by recursion in this way. We would like it to be a morphism of operads, so a family of linear maps. We set CA0 as equal to the zero map, because S0 is zero space. So the unique linear map from a zero space to another vector space is the zero map, of course. And then we define it on generators in this way, as a unique generator for each arity. So here we set CA1 of mu1 equal to the identity map over the vector space A, because we would like it to be a morphism of operads, so it has to preserve identity again. And then we set CA2 of mu2 as equal to the associative multiplication. And we set CAN of mu(n) as equal to MA composed with CAN minus 1 of mu(n) minus 1 tensor the identity by recursion, and then everything is well posed thanks to the associativity of MA, it is really easy to check. And again, we set G of morphisms. We define geomorphisms like the identity. So again, it is well defined for the same reason. Now, probably we have to prove it by induction because of the definition of G, but I think it is really easy. And again, factorial identities are obvious, and it follows from the definition of F and G that they really are with each other. It is very, very easy. So it's really basic and just linear algebra.
Sorry, just comment. I don't remember to say that, but I guess mu1 is here the one corolla, mu2 is the two corolla, and so on.
Yes, we can think about them in this
Just
way.
visual.
Yes, yes. To be honest, I don't like by which just uses trees, but yes,
Okay.
I'm more into algebra.
Okay.
But of course, we can do it, and most of people who do this stuff, they
it's computations.
yes, they prefer the use of trees. Yes, which is more visual. Okay. Okay, I think we need the board now. Any questions about the proof? It is really easy. I promise. Okay. Okay, so now we can meet the second grace of algebra, the Operads. It is very, very similar to us, almost identical in its structure. But now we would like to enforce commutativity, and in order to do that, we need to define an action of the symmetric group, which now is the trivial one. So it simply identifies operations with the input swapped. You can think about it in this way. If you have a corolla, 1, 2 is the same of 2, 1. So it's really easy. And again, we have the same isomorphism theorem. So the category of algebras with the Operads is isomorphic as a category to the category of commutative associative algebras. And actually, there is also a way to extend this kind of setting to unital associative algebras and unital commutative associative algebras, and it is really easy. We just have to define COM0 as isomorphic to the fit K and not just the zero space. So everything is general and can be extended in very quite way. Okay, and so with the tools I provided you and I've given you so far, we can easily recover the associative and commutative case, but we struggle a lot if we try to define by hands an opera which whose elements satisfy Jacobi identity, because it is an identity tree relation, and we struggle a lot if we try just to define an opera by listing its spaces and by defining an action of the symmetric group. And so the easiest way to define the third grace, the Operads Libby, is by means of generators and relations, which are very powerful tools, and they are very similar to what we do like in group theory. So I think you are familiar with them. We can define it in a more detailed way. In order to define an operand by means of generators and relations, what we do is essentially consider a family of generators. Then we consider the free object over this family, so the free operand, which is like the family of all composite operations we can obtain from generators by means of composition. And then we quotient by the relations we need in order to obtain the structure we want. But it leads us to the definition of a pre-operad. It is, I think, a definition you are familiar with because this is the analog of a pre-object in algebra. So it is here, this couple, PI, and it is defined by means of a universal property saying that if you have an assignment of generators into another operad Q, then this assignment extends in a unique way to a morphism of operads from the pre-operad over the collection of the family of generators P to the operad Q, and it is really, really easy. And the nice thing is that the pre-operad exists, and it is also unique, up to a unique isomorphism. But I think the better thing is that it is not an abstract object. It is a concrete object because a model for the pre-operad is the operad of decorated trees. They are just like trees, like we have defined them before. But here we have that vertices are labeled by means of generators. So if you have a binary operation, you can use it in order to label to corolla, for example. And so you obtain decorated trees. They form an operad, and this operad is a model for the pre-operad. So I think that it makes you understand that trees are not just pictures, but they are innate in a sense in the theory of operads. Okay, so finally, an operad O is presented by generators P and relations R if the operad O is isomorphic to the quotient of the pre-operad generated by the generators, the family of generators P, by the ideal generated by the relations R. And here, ideals and quotient is the analog of the definition you are familiar with in algebra. So an ideal is a family stable under composition, and quotient is defined in the obvious way. And this is a really nice thing because every opera that needs a presentation, it means that generators and relations is not just a trick for examples in order to build new examples, but it's something completely general. And yes, and I think it is also a sort of sanity check for the theory we are building up, because it is really similar to the algebraic theories we are familiar with and in which this kind of theorem is true, and I think that's a cool thing. And the proof is really easy. You just have to choose relations and generators, and then everything is well posed thanks to the universal property. So everything works in a very nice way. Okay, and okay, now we are finally able to define the operad Lie. Lie is defined, as I mentioned, by means of generators and relations. Here we have a unique generator, which can be put like a Lie bracket, a binary operation, and we have the obvious relations, skew symmetry, and Jacobi identity, which are this one, and they can also be drawn like trees in the obvious way. Here we just minus, and then we have Jacobi identity, which can be drawn like this: 1, 2, 3, plus. Not straight. Okay, 2, 3, 1, plus 1, 2, and then equal to 0 if you want, but in the quotient is 0. It is very easy, and again, it's the same theorem, so an isomorphism of categories. The category of algebras will be obviously isomorphic to the category of Lie algebras, and the proof is the same for us. The unique different thing which I think is really interesting, is when you try to define G, then you cannot do it by hands because you don't know how Lee is made, how what kind of spaces we have behind Lee. And so what we do is to define an assignment of generators. I just want to quickly mention this construction. We define an assignment of the unique generator mu of Lee to the Lee bracket, and then this assignment extends to a unique morphism of operads thanks to this beautiful theorem, the theorem of extension, what's here, saying that if the image, the Lie bracket satisfies relations in the operad B, so Swiss symmetry and Jacobi identity, and it's obvious because it is the Lie bracket, then an assignment of generators extends in a unique way to a morphism of operads, which was exactly what we wanted to obtain, and everything works according to universal properties. So if you define the theory in a nice way, then everything is really easy and you do not have to check anything. And okay, I don't know if you want, I can just mention a few generalizations of this theory, which I think are very natural if you understand that operads are just operations and composition. Because once you understand this, they are like very natural. If you want operations with inputs of different types, like from different sets or different vector spaces, then you can just assign a color to each set or each vector space, and then you can define composition in the same way, but now you can compose operations only if color match, and I think it's really nice. Then you have cyclic operads, which are useful, especially when you have an inner product and where you have symmetries between inputs and outputs, and you also want to swap inputs and outputs. And for example, in Frobenius algebra, this is the common setting. And props and operads, which as far as I know is the one you are more interested in, because they can allow you to model by algebra type structures, which as far as I know are the one you are more interested in, because by means of operad theory, we managed to model algebras and also co-algebras, because there exists a definition of a co-operad and co-algebra over an operad, but we are not able to control them in the same at the same time. Okay, and so we need props and operads to do that.
So you mean that for the compatibility between algebras and
yes, yes, exactly, yes, yes, yes,
right.
Yeah, maybe it's not one.
Because if you have a real algebra, you can have like maths with n inputs and n outputs, and in another you cannot have this because either you have n1 or 1n. Yeah.
Yes, yes. Thanks to our co-algebra over an operad, you can have n outputs and one input, but not at the same time n inputs and n outputs, for example. Yes, exactly.
So
yes.
Now we spoke about these three operads. So if you think about, let's say, finite number of free generators, so the number of generators is an invariant of free operad. Because like sometimes for certain free objects, for example, you consider the theory of modules. So if you don't have any assumptions on the ring over which you consider modules, the rank would not be even defined. For that you need to have something like an invariance basis number property for the ring. So somehow you could have this type of ambiguity Do I understand correctly that for Operads you don't have that, I mean, like number of generators is basically that way?
No, as far as I know, we do not have a hypothesis about the number of generators. Free operad in general is an infinity. Yes, but when you quotient it by relations, you can obtain a finite structure.
Oh, sure, I understand. Excellent.
The least number of invariants is invariant.
And seminar is almost finished. I just want to leave you with a question, which recalls what I said at the beginning. In your opinion, is operad theory just language? My answer, to be honest, is yes. Probably it is. Most of category theory is in a way just language, and most of what we do is language. But I think that it is a powerful language because it allows us to do a lot of things. And I think that language is almost never completely unuseful because a new language makes things that before were unthinkable, thinkable, and it turns mysterious definitions and mysterious theorems now natural and really easy to prove by means of operad language and operad theory. And I think it's also really cool because I think operations are probably the first thing we think about when we are young and we think about mathematics. So it is really nice to have an elegant way to describe operations and composition, and it is very elegant in my opinion. And thanks. And by means of operads, you can actually model any algebraic structure with a multilinear operation and one output. So if you think about an algebraic structure with multilinear operations and one output, you can, of course, construct an operad which models this kind of a structure. You just have to choose generators and relations, then you can do it. You struggle if you try to do this for groups, for example, because there you have the inverse, which is not linear or multilinear operation, but then you can do this for every algebraic structure with multilinear operations and one output, and it's really cool. And okay, the seminar is really finished now. I would like to thank again Thomas for inviting me, thank again my supervisors, and thank you, of course, for your attention and for being here. I'm so excited. Yes, thank you. If you have questions, I would be really happy to take them.
Thank you. Do we have questions? Maybe we can start with one question. So also some people in this audience like BB algebras. Is there an operatic way to understand them?
Yes, as far as I know, yes, but it is like a more advanced topic. But yes, I'm sure that this kind of operad exists, and maybe I can tell you some references. But to be honest, I'm not very into it.
It's a normal opera. It's not
No, not a strange one. Not a strange one. Maybe we need some causal duality in some cases, but I think that for the BB opera, we do not need it. Yes.
But so BB algebra should be an opera like a information quantization in some sense of the opera that gives best in algebras, I think. So like B0 algebra. So just yeah, the Gaussian number structure provides yeah, like the Gaussian. Yeah, it just gives you the BB the failure of the differential that given by the Watson bracket. You have to add this to
making the failure being a differential, but just like Leibniz rule.
Leibniz. Yeah.
maybe I did not stress it so much, but as commonly are really, really important also because they are the most fundamental examples of quadratic operads, which are the ones which can be cosmul. It means that they can be, we can build calculus upon them, and we can consider their deformations. They have very nice homological properties, and it is the reason why we focus on them. It is something very advanced, but everything starts from this setting.
I have a question that may be related to this. I heard somewhere, but I don't remember where, so this may be false. If you have an algebraic opera, you can attach a homology complex to it.
Yes.
Okay.
Yes.
Do you know sketchy? Can you sketch the idea or? Okay. You can send me the reference because.
So we
I
can
may be
do a lot
interested.
of things with operas. We can also define a group opera, and we can let them act on other operas. We can do a lot of things because this is really an algebraic structure itself, and we can do almost everything we can do with every algebraic structure by means of opera theory.
But I don't even know the preference for that.
It's
not below the one.
I want something where I
Don't think so.
It's actually which is pretty much.
Some of sleeps.
So passive. It's cliche.
Maybe I can try because I have on my laptop a lot of time. Yes, I read something about it, so probably in one of my books, yeah, we can find
Yes,
something.
thanks.
Okay, do we have more questions? Maybe I can ask another question. This was actually a question that Marvin posed at some point. So you know that so we were speaking about Lie algebras and algebras, and of course, like we can find factors between them. Like if
Yes,
you have a Lie algebra, you can build a universal enveloping algebra, which is an algebra, and vice versa. Like for every algebra, you can get a Lie algebra, just taking the vector space with the commutator, right? And so is there a way to see these functors on the level of operads? So that, I don't know, proving that these functors exist.
The one that
Or
I
like
easy.
very high.
Yeah, exactly.
Yeah, but it's a bit small.
to be honest, there is a way to turn an associative algebra into a Lie one by means of a factor of operads, but the one you mentioned, yeah.
I think it's possible, but you need to
Yes.
modify your opera a bit. Like perhaps it's a bit more and it's the same.
Great. So are there more questions, maybe also from the online audience? Doesn't seem to be the case, then let's thank the speaker again.
Hi, Thomas. Can you hear me? Can you hear me?
Yes, yes, yes.
I just a comment. I guess you maybe know, but a morphism of operads gives you a map of gives you a functor of the algebra of the categories of algebras in the opposite direction.
Can you repeat your comment?
If you have a morphism of operads from P to Q, you get the functor from Q algebras to P algebras.
Yeah.
Yeah, and that's the so there's a morphism of operads from Lie to us,
Yes.
which yeah.
But the other way.
I don't know if this was the question.
I probably think that the question was in the other direction. Yes.
It was in that direction.
Yes, but I think the answer is yes. We can.
But so
Yes,
you want to.
but not easy. Yes. Exactly.
But wait, but so in that direction you mean that if you have a Lie algebra, you can make an associative algebra out of it? as by taking the universal enveloping, you mean?
Precisely.
I see. Thank you.
Thanks, everyone.
Okay, thanks. I don't know.